second lecture in this series on resurgence and differential equations and effective summation formulas. Over to you, Gerald.
Thanks, David. All right, so this is the second lecture. Yesterday, we did a lot of work in all the lectures on the area function. And the theme of this second lecture is going to be to see what happens when we generalize from a linear equation to a nonlinear equation. So there'll actually be several interesting overlaps with what Adri was talking about. And I'm going to specifically concentrate to start off with a nonlinear generalization of the area equation. So just some general remarks to start off. If we have a linear ODE of nth order, then there are typically n non-perturbative exponential terms, which we can identify with n Borel singularities. Once we go to a nonlinear ODE, as Adri just mentioned, actually, as soon as we have one exponential, we immediately have infinitely many exponentials, just because of the nonlinearity. As soon as you generate an e to the minus x, a nonlinearity will generate e to the minus 2x, and so on. A very trivial example of that is that if you take two independent solutions to a second order linear equation and then take their ratio, you will clearly generate an infinite expansion in exponentials. A second new feature is that the Borel singularities, instead of just being one singularity or two isolated singularities in the Borel plane, each of these will typically be repeated in integer multiples of one another because of this nonlinearity. Actually, I have in parentheses there the word certain, because they don't actually have to be all integer multiples. I'll show you an example where it's odd integer multiples, and they can even be examples where it might be an n squared multiples of the leading one. And that can happen because certain residues vanish with special symmetries. Another interesting new feature in the nonlinear case is that there can be resonance between different Borel singularities, and that can produce logarithmic terms in the trans series. Here, x is the variable in the differential equation, and I'm going to be expanding around large x. And these also become iterated because of the nonlinearity. And so now, in addition to the powers of 1 over x and the exponentials, say e to the minus x, e to the minus 2x, etc., we also now generate powers of logarithms of x. And this then generates a much more general form of the trans series along the lines of what I mentioned at the very beginning of the lecture yesterday, this fact that the trans series is built out of these three building blocks of powers of inverse powers of x here, exponentials in x, and logarithmic terms. Another new feature is that the Stokes phenomenon becomes a lot richer and a lot more interesting. Instead of just sweeping through one singularity and picking up an exponential at some point, we can now have infinite numbers of them, and we can have the so-called nonlinear Stokes phenomenon. And I'll show you some examples of how this works in a few cases. Now, a special class of functions that are extremely interesting, and we've already heard something about ARAW01, and I'll mention several of the ARAW. You can really view these as the special functions of nonlinear ODEs, and I've put in the references a very, very nice review article by Peter Clarkson, which I recommend to anybody who's not familiar with the ARAW equations. There are many applications in mathematics and physics, and they're extremely interesting functions mathematically, as well as having these applications. And I urge you to look at that article, and also on the digital library. There's a lot of information about this. Having said that, I really want to make a comment here. There's a misconception amongst some people, is that integrability, although it's extremely interesting and rich subject, it's not required at all for resurgence. And you can see that in two ways. The proofs of resurgence in ODEs never invoke the concept of integrability. It's simply not required. And you can also see by examples. You can take some non-integrable equation, and the procedure and the techniques for resurgence follow exactly as is. And I'll show you some examples of that. So let me begin by taking what we did yesterday about the area function and just making it nonlinear. And the easiest way to do that is to consider what's called the second Penalty equation. And actually, it's a specialization. I've neglected the constant term that could be added here. And so this is the linear area equation. I've added a cubic nonlinearity. This innocent looking equation appears in an impressive list of applications in mathematics and physics and even beyond. It has a certain universality to it that I will comment on as we proceed. But the theme, it's a vast subject. The theme of what I'm going to talk about today in this lecture is to illustrate how this nonlinearity changes the discussion that we went through yesterday. So let's just look big picture asymptotics. What are the possible eventual asymptotics? First along the real axis, and then we'll go into the complex plane. So we could imagine looking for a solution where as x goes to infinity, y becomes very small, say exponentially small, in which case we can neglect this term relative to the others, and we're just left with the area equation. And so the solution will start off being the area function. I choose at this point to have a decreasing function as x goes to plus infinity. It's a homogeneous equation now and linear, so there'll be some constant. And then there's plus dot dot dot, which is what we'd like to understand. So it's self-consistent because this is indeed exponentially decreasing. So I can neglect y cubed with respect to y. On the other hand, as x goes to minus infinity along the real axis, I could choose to balance these two terms, in which case I have this square root type behavior. And so I see a question. Yes, I'll talk about that at the end. I'm choosing this one for simplicity and because it ties in with our discussion of the area function from yesterday. This balance gives me instead a simple square root type dependence with a plus or minus sign. And notice there's no constant here. This is similar to what Adri just mentioned. The general solution to this Penlever equation, even with that constant term that I neglected, is meromorphic. That's in fact what is meant by Penlever integrability. And the expansion around any movable singularity is just a first order pole. And the expansion generates eventually one further constant. And then all the other coefficients here are just functions of this parameter and this parameter. So these are the two boundary condition parameters for the general meromorphic solution. So that's interesting. There's also an interesting numerical instability that if I integrate starting at large x and I integrate in this direction, I can tune this coefficient here very sensitively about the value 1. And if it's any amounts larger than 1, then I develop a pole. And if it's any amount smaller than 1, I develop a sort of area-like oscillatory behavior. But if it's exactly 1, then it will hug this separatrix here. So here's a plot of when it's equal to a half. And you see it looks very much like the area function. So here's an exercise to start off. If you're not familiar with these, you can first verify that this is in fact the expansion in this equation. And then you can check, so the special thing is here that the only singularities are poles. There are no logarithms and no essential singularities. And if you change this y cubed to y to the fourth, you will see that that fails. And nevertheless, all of that I'm saying about resurgent transeries analysis can be repeated, even if it's y to the fourth here. Now, into the complex plane, there's this, as I mentioned, there's this very special solution when this coefficient of the area function in the positive x direction is exactly 1. There's this very special solution that matches that asymptotics with this separatrix asymptotics. It can go up or down. That's a trivial choice between plus or minus. In the complex plane, here are the poles. The blue and the yellow refer to the sign of the residue. And they fall within this pi over 3 wedge here between pi over 3 and 2 pi over 3 and minus pi over 3 and minus 2 pi over 3. So that's a special feature that is this extremely fine-tuned solution to the equation. If you change this coefficient away from 1 here a little bit so that it behaves like sort of area-like oscillatory in the negative x direction, you see that there are further poles out in this region here. And I've taken this from a nice review summary by Thornburg et al. So there's a deep reason for that. There's a relation that was uncovered by Boutroux more than 100 years ago, I think, is that if we define a new function, just clean this equation up a little bit, put in a square root here, it looks like this. And now if we change variable to the appropriate variable, which we recognize as this action-like variable, often called the Acal variable in the Resurgence literature, this equation becomes this. And now we recognize this as the equation for the Weierstrass P function. This is a nonlinear equation that we can solve. And the solution has this regular lattice of poles in the complex plane. And this is a perturbation of that at large Z. So that means that asymptotically at very large Z, magnitude of Z, there's an approximate solution that is essentially in terms of this Weierstrass P function. And by tuning very delicately the parameters of that P function, that can move these poles around. As you know, the P function, you can push the poles off to infinity and just be left with trigonometric or what's the other one? Hyperbolic trigonometric functions. So here's a plot just of the general pole structure. I hope you can see these dots here. But this is this regular 2π/3 structure that's just governed by the basic symmetries of the equation. But closer to the origin, of course, this is deformed because here we neglected this type of perturbation. Okay, so let's go back onto the real axis for a moment, and let's treat separately the positive x direction and the negative x direction and try and build systematically the trans-series type structure in the along the real axis first. So remember that positive x, we have this choice that we take the area function with some parameter here, and now we're going to fill in the plus ... dots here. So first of all, notice that we can write this equation in this integral equation form. So clearly, this is the leading solution, and here's the correction. It's going to go to 0 as x goes to infinity because these are exponentially decreasing. To verify that this is a solution, just differentiate once. Well, you get ai prime, that's fine. When you differentiate the lower limit here, you just get 0 because this vanishes. And then when you differentiate inside, see that this is x. This factor could in fact be taken outside of the integral, as could this. You just get ai prime and bi prime. So now let's differentiate again. We get ai double prime, so that's just x times ai. So that's x times this part of the function. And now when I differentiate the lower limit now, remember there's now a prime here and a prime here, so I just get the Wronskian. And that Wronskian is something like 1/π if I got my factors right. And so what you get then is you generate automatically this y³ contribution. And then when I differentiate inside the integral, I now have ai double prime and bi double prime. That just gives me a factor of x. So I generate xy, and the y³ came from the Wronskian piece. Right? So this is an exact integral representation of the equation. And now I can iterate this. I just insert y into the y³ here. And so you see that the next correction will be sigma cubed with an ai³ here. And then I can systematically extend that. And so what we learn is we generate a trans series which has all odd powers of this sigma parameter. And you can think of the sigma parameter as a counting of these of this grading under the exponentials. And these functions here have these nice simple iterated integral representations. The leading one, of course, is just this guy ai. The next one will be where this y is just replaced by ai. So it has these two terms here. And the next one, I'll have to insert this one into the integral. So I get nested type integrals. But now the asymptotics is very easy now, because if we look at the asymptotics, first of all, we learned yesterday in gory detail about the asymptotics of ai. And so we can apply that also for BI, and we see that this is an exponential, say, the cube of the decreasing exponential, and this is one increasing guy. So this will be decreasing, say, the second power of the decreasing exponential, multiplied by that, that will be the third power. That's that 3 here. Over here, this is the fourth power of the decreasing exponential of the array, but I'm multiplying it by one increasing exponential. So also this is a third order, and so on. You can continue this through, and you see that the odd powers of sigma are multiplied by some function, which is, say, the odd power of the standard airy exponential factor multiplied by some other junk, which we can easily generate because we know the expansions of all these integrands here. So there's a very systematic, straightforward way to generate this trend series as x goes to plus infinity. So the net result is we have this standard airy factor, including, you can choose to normalize with this x to the 1/4 here, raised to odd powers, and then multiplied by some asymptotic series for each value of n. And the form of that series has some coefficients labeled by the n, of course, and the index of the coefficients is m, and in inverse powers of the natural variable, which is this x to the 3/2. And we see that there's just one parameter, this so-called trend series parameter, which came from the original homogeneous part. Interestingly, there's no formal series solution here. The first contribution is automatically exponentially small. That was our choice in making this leading part be the airy function itself. Now we can use this. There's an interesting numerical test we can do here, is we can go back and evaluate y at 0 and y prime at 0, because it just means we have to evaluate this at 0, evaluate this at 0. Well, that's easy. We just have to now integrate from 0 to infinity, 0 to infinity. The airy functions at 0 and the derivatives have simple expressions in terms of gamma functions. And so we can evaluate this, just say, for example, taking the first two terms, we have ai of 0, and then the first correction will depend on ai of 0 and bi of 0 multiplied by these weird integrals, which I put in for the benefit of our chairman who loves these types of integrals. And if you do the same thing for the derivative, we get these expressions for the value of this trend series, which was generated at plus infinity, but now all the way down to x equals 0, just taking the first two terms of this extremely simple trend series expansion. And we can now compare these, and I've chosen sigma to be +1 here in this expansion in order to compare with this Hastings-McLeod solution, this special separatrix matching solution. And if we go back, we see that these values quoted on in this numerical paper match very precisely these just from the first two terms. So this is a very rapidly converging approximation in the positive x region. So that's the structure of the trend series on that side. And now let me turn, if there are no questions, let me turn to the opposite direction where something very different happens. So in the x goes to minus infinity direction, I'm going to choose to study the solution that in the x goes to minus infinity direction hugs this separatrix parabola. And that involves balancing these two things. So the leading piece is this minus x over 2. I've shown the plus sign out front because there's no real difference. They're just symmetrically related to one another. And we can just insert an ansatz in inverse powers of this x to the minus x to the 3/2 and just put it into the differential equation. There's a simple recursion formula to generate as many terms of this series as we want. There's no closed form formula for these coefficients, but it's a simple iterative procedure to generate them. But we see, now this is very similar to the example, Pennebaker example that Adri just discussed. There's no parameter here. This is a second order equation, and I'm presenting you a solution, a asymptotic expansion that has absolutely no parameter in it. So that tells you already that something is missing. And the something that is missing is some non-perturbative corrections, these exponentially small corrections. Another way to see in Borel-style language that there's something missing is that we'll learn that these coefficients are actually factorially diverging. By this point, that shouldn't be surprising to you. But they're also non-alternating. And if you remember the discussion from yesterday about the Borel transform, and in particular on the incomplete gamma function examples, that's very often a signature that also something is missing, because now we're integrating in Borel language, we're integrating along a line where there are singularities of the Borel transform, which we have to somehow resolve. So now we can apply some general argument, and here you'll see that there's no reference to this being an integrable equation. Let's consider a general nonlinear DE where we have some differential operator on the function is equal to some function of the some nonlinear function of the function itself. They could actually have been y primes and things in here. I didn't type that correctly. So the formal perturbative series satisfies this equation, obviously, satisfies it term by term. That's how it was generated. But we can extend this to include the first non-perturbative trend series correction. And as Andrew mentioned, it's important here to be able to control the fact that this really is exponentially smaller. But this gives us a very simple procedure to now expand to, say, first order in this term, regarding this as smaller than anything here. And this original nonlinear equation now separates into the original equation in black, which we've already solved, remember. But the equation for this extra piece, you'll notice, is linear. It's just this linear operator, and there's just y here. And we've just got the derivative of capital F, but evaluated on the formal solution. So this is a linear and homogeneous equation for this. And there's a very simple pragmatic way to solve this, which involves just making an inspired ansatz, where we take this to be some exponentially small contribution in the right variable, this critical variable, the x to the 3/2 variable, with some, at this point, unknown parameter gamma, and some power of that variable. Of course, the 3/2 is not so important here. We could absorb it into beta, but let's keep it to be this critical variable. And then an expansion in inverse powers of that. And we can, and since it's a homogeneous equation, we can allow for an overall coefficient. And now we just insert this into this equation in red here, and the first terms will immediately determine gamma, beta, and then if we push it further, we'll generate a recursion formula for these coefficients. And I stress that this procedure can be applied in great generality to other, I'll deal with questions later if you don't mind, to other nonlinear equations. Another thing that I'd like to comment on before I show you how this works in this Penave-2 example is that if we now proceed to, say, the second order, these higher exponentials, this will of course generalize, all those terms solve linear equations, and that means that we've reduced the problem to something where we know a lot. We can actually analyze this whole ladder of linear equations for these trans-series elements. So let's see how it works for Penave-2 after those general comments. So here's the structure of the original formal series, what I called now Y0. The ansatz, as x goes to minus infinity, is now going to be a sum over these trans-series terms. So these are going to be graded exponentials. And simply inserting this into the equation and expanding matching powers according to this grading, which you can just do systematically by matching powers of this parameter sigma, gives you a tower of linear equations for yk. And the first one is linear and homogeneous, as I just mentioned on the previous slide. In this particular case, of course, the linear part doesn't change. There's just x times y1. But when I expand this to leading parent y1, I pick up a y0 squared times y1 term with a factor 6. If I now go to y2, an important comment is that for y2, it's of course linear, but now it's inhomogeneous for the second order equation. So I have this same linear piece here, but now I've picked up an inhomogeneous term. So again, some of the comments that Adri made about the importance with this inhomogeneous contribution become relevant in general in these trans-series expansions. So let's solve, first of all, this equation for the first exponentially suppressed trans-series contribution. And so here's the equation. I know as many terms as I want here. And so I just write down the first few pieces here. If you remember that y0 began with minus x over 2 to the square root. So y0 is, sorry, here's y0. y0 squared is minus x over 2, that leading term. So 6 times that is minus 3x plus x gives me a minus 2x. That'll be important. And then there are corrections going in inverse powers of x. So we make this ansatz here using the natural variable, which is minus x to the 3/2. And now something interesting happens. We put this into this equation, we will immediately see what gamma is and what beta is, and we'll see what these plus dot dots are. And matching terms, this is what we find. So first of all, there's the overall constant because it's a homogeneous equation. But you might be surprised by this root 2 here. Your first naive guess would have been that this would be e to the minus 2/3 e to the minus x to the 3/2. It's actually minus root 2. This root 2 is not a misprint. And it comes from the fact that there's this 2 here that came from contributions from here and from here. And that follows through in these expansion terms also. And we can generate these coefficients systematically by a recursion formula. Now I stress that this is extremely easy to implement, and you can do exactly the same procedure with any nonlinear differential equation you want. If you have a higher order nonlinear differential equation, you just have more possibilities for these coefficients here, gamma. There can be different leading exponentials. So let's look at this from the resurgence perspective. Here I just recall the first coefficients of this formal perturbative series. So this is even before we get to these exponential terms of the trans series. Remember that we can generate systematically as many of these coefficients as we want, but there's no closed formula like there was in the Airy case yesterday. So that's why I set the exercise for the Airy case to actually study the large order growth numerically, even though there is a closed formula. Because in a case like this one here, there is no closed formula, but you can still apply exactly the same methods numerically. And you can learn that the large order growth of these coefficients is 2n factorial, essentially, with a -12 offset. And there's this power of this action parameter, the root 2 over 3, with this mysterious root 2 factor that has appeared. And you can generate the subleading corrections numerically using ratio tests and Richardson extrapolation and standard methods like that. It's very easy to generate many of these terms. In fact, that's an exercise on the next page, I think. And there's this overall Stokes constant, which you can also generate to many digits of precision. Now, the point I want to make is that we can now go and look at our solution to this y1 equation. Remember, this is the equation for this is the linear homogeneous equation for the first trans-series exponential term. And again, I can generate zillions of these coefficients here in a very quick time. And I can look at them and look at these, and you will notice that this generic relation between the large order growth, the subleading corrections to the large order growth of the coefficients of the formal perturbative series solution match the coefficients, the low order coefficients of the expansion around the first exponential term here. Right, we see this, that the power here is now not 2 over 3, it's 2 root 2 over 3, and that comes out in the power with the large order growth. That's related to the location of the first Borel singularity. And then these subleading coefficients here in the asymptotic series that multiplies the first exponential match the subleading corrections to the large order growth. So this is this duality that I mentioned yesterday between the trans-series resurgence structure in the x variable for the actual function and the trans-series large order behavior in the n variable, which is the order of the expansion. So this is just the first term in this trans-series. This is the first exponential term, and there's a whole tower of other ones. And this structure continues to all orders in that trans-series. And that's characterized beautifully in this set of Écarts-Bridge equations that Daniele will tell us about in later this week. So here's an exercise to generate from the recursion formula many terms, where many probably means 50 or 100, it's not difficult, and then just confirm that large order growth. And think about why you should have been able to say in advance why it's gamma of 2n, not gamma of n. There's a very simple argument of why that is true. And this overall coefficient you should be able to identify in terms of pi, and then lastly confirm this correspondence, this duality between these coefficients here that both Chris and Adu talked about. Okay, so just to summarize what we've learned so far about this Penlevet-2 solution, I stress this is a very special solution to a specialization of the Penlevet-2 equation. But I mention it for a good reason, because this shows up in many, many applications in physics, and it will show up in something I'm going to discuss next. The new phenomena here compared to the linear area equation, there are many things that are similar to the area equation, but there are also many things that are different. So first of all, we see that the type of trans-series as x goes to plus infinity and minus infinity is completely different. Whereas for the area function, on one side we had this, e to the minus 2/3 x to the 3/2 times something, and then the other side we had, okay, we had two exponentials, the sinusoidal type behavior, but it was basically e to the I 2/3 minus x to the 3/2. There was no change in the coefficient up here in the exponential. Here now we have very different structure as x goes to plus infinity and minus infinity, and that's because it's a consequence of this nonlinear Stokes phenomenon, that now when we're rotating from plus x to minus x through the complex plane, we're sweeping through an infinite landmine region of poles, and all sorts of interesting things happen when you cross this pi/3 wedge full of poles going from plus infinity to minus infinity. Also, we see that at x goes to plus infinity, it's odd powers of this basic exponentially decreasing term, whereas here it's all powers of this exponential term. Here we see also that there were relations between the coefficients of these different fluctuation functions or asymptotic expansions multiplying these exponential contributions. And in physics language, this would be seen as a so-called condensation of instantons as you go through this complicated nonlinear Stokes phenomenon as you go through pi/3 and then 2pi/3. There is a systematic way to deal with this. Actually, there are several systematic ways to deal with this. One particular one that is very close to this trans-series structure that I discussed is called transasymptotics. Unfortunately, I won't have time to talk about it today, but hopefully we'll have some discussion of this method during the program later. So just here, I just flash up again this interesting structure in the complex plane. Here's this pole region that we've swept through going from plus infinity to minus infinity by rotating around here or around here for this Hastings-McLeod solution. The more general solutions to this Penlevet-2 equation, of course, aren't fine-tuned to hug the separatrix. They would go like this. There's still a very beautiful exact connection formula connecting this solution to this solution. And in the complex plane, we see that as a result of these the nonlinear Stokes form is even more interesting because of the appearance of these other singularities in the function itself. So this is a very rich subject, and I could talk forever and ever about it, but I'm going to switch gears now to another application. So the main theme here is to notice what changed when going from the linear area equation to this nonlinear area equation. So now I'm going to continue in this theme of studying some of these Penlevet equations. And again, I have to emphasize the fact that this isn't because resurgence only works for these integrable equations. The reason is that they turn out to be interesting in problems in physics very often, but also there's a lot of analytic information that is already known about these equations. So if you're going to discuss things like exponential asymptotics or analytic continuation for using Borel summation, a natural place to start is to start with interesting non-trivial problems where you have something that you can really compare with, to really test whether your methods are precise or whether maybe you're just missing some numerical weirdness of the problem, to be able to identify that these exponentially small contributions are, first of all, genuine and that they're accurate to the exponential order we want to probe. So that's the caveat of the reason why you'll often see papers about resurgence discussing things like Penlevet equations or integrable equations in general. But recall that the methods that have been developed for the resurgent trend series do not require that integrability. So at the risk of creating confusion in that direction, I'm going to discuss another Penlevet equation. Now, one of the Penlevet three equations. So for the mathematicians in the audience, there's a well-known model in the physics literature called the Gross-Witten-Modier unitary matrix model. It actually plays a big role in the theory of random matrix theory, and it has applications in combinatorics and just as an interesting system in asymptotics in general and in probability theory, but it came from the physics literature. So here's a partition function. It's a function of two variables. T is some real parameter. N is, at the starting point, it's a positive integer. It's the dimension of unitary matrices that we're integrating over. So this is some sort of Haar measure integrating over n by n unitary matrices. And the integrand is just an exponential of, something that's mimicking the cosine, if you think of these as e to the I Hermitian matrix. So there are two parameters. There's the t variable and the n variable. And in the physics language, this would be the 't Hooft coupling T and the matrix size n. And what was found by Gross and Witten and by Radier more or less simultaneously was that there's a third order phase transition in the system at n equals infinity. So the idea is to study this problem as a function of t and as a function of n, and particularly looking at the limit that n becomes large. So this will turn out to be an example of what Adri discussed of this parametric asymptotics. We're now going to do asymptotics. We have a choice of doing asymptotics in t or n. I'm going to discuss the large n asymptotics. So 1 over n would be like the epsilon that Adri was talking about, but we're going to have a differential equation in t, which has this parameter n in it. We'll be studying n goes to infinity. And so at n equals infinity, there's a quantity called the specific heat, which is related to the second derivative of the log of this. It has a kink at some particular value. Now, I've changed my normalization with respect to their conventions. I've put in an extra factor of 2 to put this transition at 1 instead of at 2. But the point is that there's some sharp kink when n equals infinity. Now, this integral can actually be performed. So this is sort of an example also that Chris was talking about, a multi-dimensional integral. And so clearly we learned that these multi-dimensional exponential integrals are inherently interesting in their own right. But here we're trying to take the limit as n goes to infinity. But this is a very special integral because of the group structure here, that these are unitary matrices. These integrals can actually all be done in closed form. And this partition function is the determinant of an n by n matrix whose entries are just Bessel functions. These are the modified Bessel functions, and the jk entry of this matrix is ij minus k, evaluated at n over t. And so we know a lot about the asymptotics of these functions, so we should be able to say a lot about the asymptotics of this. But of course, the problem is that when you're going to study large n, a determinant is not a very friendly thing as n becomes large. So it would be better to have a nicer entry into this problem. And such a thing exists because there's a quantity which would be what we would write as the expectation of the determinant of u. So you just insert a factor of the determinant of u here and do the integral. And that integral can also be done. And that function happens to satisfy a particular nonlinear differential equation, which is in the Penave-3 class. So for the experts, this can be transformed into the Okamoto form of the Penave-3 equation with a particular choice of the parameters of Penave-3. Don't worry about that if that didn't mean anything to you. Just look at this equation. We have a nonlinear differential equation. This delta is to the power of 3. Here's this inverse 1 over 1 minus delta squared. The derivatives, these primes are derivatives with respect to t, but you see that n appears as a parameter in the equation. This delta is something from which I can construct all of the other interesting stuff, the partition function, the specific heat, the free energy, et cetera, through this Toda-like equation relating to the partition function. So basically, I'm going to work with this delta, just knowing that all of the trans-series structure I derive for delta will be inherited by the physical functions like the partition function and free energy, et cetera. So if we're interested in large n, the natural thing to do would be to make this type of expansion that Adi proposed. So remember, 1 over n is like his epsilon. So we just have some formal expansion in inverse powers of n, but then we should expect the possibility of possibly some trans-series type contributions, e to the minus n, e to the minus n times some other function of t with another series, and so on, to all orders. And the physical observables will inherit this trans-series structure just through these types of nonlinear relations. And the point I want to make here is that just like in the Penave-2 case that we just discussed, the structure of this trans-series will actually be completely different depending on the value of t. And that will be a way to characterize this phase transition at t equals 1. The structure of this trans-series is going to be totally different for t bigger than 1 compared to t less than 1. So here's just a plot. You can just easily evaluate these things even in terms of these determinants and just plot it as a function of t for various values of n, I guess 1, 2, this I think went up to something like 20. And you see there's this development of a kink here and the n goes to infinity limit. And so this is the interesting stuff we'd like to understand here. But you see there's decreasing rapidly at large t. So we can use that now to study the asymptotics in t being either bigger than 1 or less than 1 as n goes to infinity. So this is this case of parametric asymptotics and parametric resurgence. So here's an exercise. It's not particularly difficult. You can just take in the large t region, you can neglect the higher order, the nonlinear pieces in delta, and you see you just pick out something which is essentially a Bessel equation, and the solutions of this linearized form are just this jn of n over t, and this one eventually blows up. So this is the solution that is going to match this type of behavior here, and then show that you can use that to build iterate a trans-series using this integral equation technique that I mentioned for the Penave-2 example before. Whereas when t is less than 1, there is no exponential decrease of any sort. It looks like a nice algebraic behavior. And you can see that also from the differential equation, because when n is infinitely large, all you're doing is balancing this term against this term, which immediately tells you that delta goes like square root of 1 minus t. And that's this red dotted line here that the solution is hugging as n increases. So this is a simple exercise, but it shows you that these nonlinear differential equations are not as scary as they might seem at first sight. Now we can push this basic starting point further. And so this is the formal, say, epsilon expansion that Andrew is mentioning. This would be the leading large N expansion. So this is when physicists talk about large N expansions, this is usually what they mean. The coefficients can be generated absolutely straightforwardly, iteratively from the differential equation. These are just functions of t that you can actually solve for very easily. But then there's the possibility of this exponentially small piece and then all powers of this exponential factor, each of them multiplied by another series. And the point is that because you have an explicit differential equation, it's really a triviality to insert an ansatz like this into the differential equation and then solve for this exponential, solve for the prefactor, and then solve for these coefficient functions of the 1 over n expansion around this exponential, and then to iterate this to higher and higher orders. Of course, it becomes messier and messier as you go to higher orders, but it's completely systematic and actually quite easy to implement. And so, for example, this action, this on the weak coupling side, so this is t less than 1, one side of the phase transition, this function takes this explicit form. It's very easy to get from the differential equation. Interesting fact is that this prefactor is this 1 over the square root of the derivative of this, just like the familiar WKB type behavior. And then you can generate these guys. And so here's the first coefficient of this 1 over n. I can generate many of them. I just write the first one here. And you see it's a relatively simple function of t. Here you see, again, this is similar to what Adri mentioned, the singularities here at t equals 1. This is the signature that that's the transition. That's where this nonlinear Stokes phenomenon is going to happen in this problem. And now, knowing this, we should, thinking about this in the light of what we've been saying about resurgence, we would suspect that this term here should be related somehow to the large order growth of these coefficients here as a function of t. But we can generate many of these, and so we can check. And in fact, indeed, the large order index growth of these things for any t less than 1 is factorial. And the power is exactly this function, this weird function of t raised to the appropriate power. There's an overall 1 minus t come from balancing this with this. And then there are subleading corrections where you remove one of the factorial indices and remove a factor of the weak coupling action. And the coefficient is itself a function of t, and it matches exactly the function coming in the low orders of this term. And you can continue this to higher and higher orders. There's a very rich structure here of resurgence relations, these so-called bridge equations between the different terms in the trans series. The difference here is that we're developing a trans series in the asymptotic parameter n, and all of the coefficients and trans series terms are themselves functions of the other variable t. And yet the resurgence structure still holds. But now if we look on the other side of the phase transition at t bigger than 1, it's completely different. So it's actually a little bit like the Penalty 2 example in the sense that now on this side, it's immediately exponentially small. And now we have several options here. We have the approximate linearization gives this Bessel function. And now we're looking at large n. And so there are several things we can do. There's this so-called Debye approximation, which has this exponential form here with corrections. And then this strong coupling instant-on action in physics lingo would be this particular function here, which you can just get from the Debye expansion, just from studying the Bessel equation. And in the language of the original integral over the unitary matrices or over the eigenvalues of those matrices, this corresponds, going from t less than 1 to t greater than 1, corresponds to a flip in the saddles of all those eigenvalue integrals. So it's an example of what Chris was talking about, but in this infinite n limit. Of course, we know if we're studying this thing, a much better thing to do would be to use the uniform large N approximation, which is where this thing is actually written in terms of an airy function itself. And so we see this airy function showing up again and again and again. It has the universal behavior of a, so we know that the airy function is a universal behavior near a turning point in WKB, and so doing uniform WKB is built on taking an airy function of some other function. So this is like an infinite dimensional nonlinear version of that using uniform WKB for this nonlinear differential equation. Another interesting thing is that the region around the phase transition can be studied using what's called a double scaling limit. So this is a very beautiful property of the Pennebaum equations, that there's a reduction cascade in the Pennebaum equation, starting at the Pennebaum 6 level, which has many parameters in it. You can tune these parameters and the variable and take certain limits of the expansion points. And when these points merge, they can become singularities and the structure changes, and you reduce to the other Pennebaum equations, just like happens in the familiar special functions. And so we can zoom in on this region where t equals 1 by defining a new variable that scales in this particular way when n becomes large. And we can define a new function, which is this function reduced to a function just of this, so that as n goes to infinity, we zoom in closer and closer to this transition point at t equals 1. And if we do that and insert this into the nonlinear equation for delta, this is this equation here, we can just insert this scaling relation now into that equation, take n to infinity, and lo and behold, it reduces to the Pennebaum 2 equation in this scaled parameter n. And the 2/3 and 1/3 showing up here are obvious scalings from the underlying airy structure here. And this is related to the property of the airy function as a reduction of the Bessel function that should be familiar from the ordinary special functions, the linear problem. The net result of this is that in the immediate vicinity of this phase transition, at this thing that becomes a kink when n is equal to infinity, but is not a kink when n is not equal to infinity, but is becoming sharper and sharper as n goes to infinity. If you're interested in approaching that limit carefully in this large n limit, up to this exponential precision from this trans-series correction, you discover that not only does this equation reduce to the Pennebaum 2 equation, the solution, the relevant solution for this phase transition is indeed that particular one that we were talking about before, the one that was an airy function on one side and then hugged the separatrix on the other side. And that's because what we're doing here is basically matching this exponential behavior here with some simple algebraic type behavior on this side. So it turns out not only does the equation reduce to this Pennebaum 2 equation, we see that it also selects this particular solution, which is the one that I described earlier in the talk. And what that means is you can match the trans series in the full finite n problem, which is different on one side of the transition and on the other side of the transition. In this reduced language, t being bigger than 1 or less than 1 refers to kappa being positive or negative. So it matches onto the different trans series structure of the Pennebaum 2 equation when kappa is either positive or negative, as we discussed before. And everything shouldn't be a big surprise that everything matches to all orders in the trans series expansions. Okay, so that's a nice consistency condition. And I should say that these types of coalescence cascades have now been studied in great detail, both in the physics literature and the mathematics literature. And it's an extremely rich subject and all sorts of interesting relations to integrable models and applications in probability theory and in combinatorics. And it can all be understood in this trans-series type language. So here I have some plots, I guess, of the way it behaves near this phase transition, because I've called it kappa instead of chi instead of kappa. You see it goes nicely through the Hastings-MacLeod solution, whereas the Debye expansion has this fake singularity, just like ordinary WKB has this fake singularity at the turning point. So this has a physical interpretation in terms of, so this maybe won't mean too much to some of the mathematicians, but to physicists, there's this beautiful argument due to Li and Yang about how you can develop singularities in the thermodynamic limit. So we can think here of n going to infinity as a sort of thermodynamic limit. And at any finite n, there is no phase transition, but the partition function has zeros, but they're complex zeros. And the idea of Li and Yang is that as n goes to infinity, these complex zeros will pinch the real variable axis, this would be t here, at some particular point, and that will be an indication of a phase transition. And so this was some conjecture of how it would behave. But because of this relation to Painlevé 2, we see that here, these are those Painlevé 2 poles that I showed you before in this pi/3 wedge. And they just scale towards the critical point, this phase transition point, with this scaling of 2/3 as n goes to infinity. So it's a very beautiful and explicit demonstration of this Li-Yang idea. Last slide for this lecture. I just want to make a general comment here, because there's some really extremely beautiful, moderately recent work about Painlevé 6. So in principle, because of these cascades, once you understand Painlevé 6, in principle, you understand all of the others because these coalescence limits can be taken. It's a bit of an exaggeration because these coalescence limits are in themselves very interesting and lots of interesting things happen. But there's a remarkable result to my mind in this recent work by Gamion, Yogov, and Vesovi. Jimbo had already noticed many, many years ago that the so-called tau function, just think of this as some particular form of the solution of the Painlevé 6 equation, has a particular expansion in certain powers at its critical points. But what was recently realized that this expansion around any of these critical points could actually be written to all orders in closed form. And the building blocks of this closed form expression, these Painlevé 6 equations are all convergent, was in terms of things coming from conformal field theory in quantum field theory. So there are certain objects that are very well studied in quantum field theory. These are some known combinatorial coefficients. The thetas are parameters of the original equation. S and sigma are the two boundary condition parameters for the solution to Painlevé 6. And these functions of T here are these conformal block objects that are very well known in conformal field theory. So this is both a remarkable result, but also a remarkable relation between Painlevé 6 and this conformal field theory subject. But this formula also immediately shows resurgence, because this sum over n is an instanton sum. These can be thought of in the appropriate direction in the complex plane as exponential instanton factors. So n labels the order of this exponential expansion, order of, say, the trans series. And so what you see is that if you know these functions when n equals 0, so that's the perturbative solution, if you know them when n equals 0, then you can write immediately any term in this instanton expansion. So this is an extremely explicit, interesting example of resurgence in the sense that you relate all orders of this trans series to just one of the orders, namely the original one. So I will stop there. Thank you.
Thank you very much. I shall applaud you on behalf of everyone. I'd also like to congratulate the speakers on how nicely their ideas gel together. They did yesterday and they have done today.
Yeah, it was purely accidental. But
maybe it's because of the organization of the conference as well. Yeah. There were two questions which accumulated, but I think you deal with them. One was what would change in the Panelet equation if you hadn't put the constant equal to 0?
Yeah, so there's a very interesting structure. So in the complex plane, there'll be more structure of the poles. For when that parameter is an integer or a half integer, there are actually solutions, special solutions in terms of special functions. It's an extremely rich landscape of possible solutions. But the underlying statement is the Boutroux statement that the solution is always asymptotically, well, it's always a meromorphic function, but it's always asymptotic to this Weierstrass structure. The interesting things happen when you tune those Weierstrass parameters to very special values and push poles off in certain directions, or if you, well, that's how you make it special. Or if you look closer to 0, where it goes away from the asymptotic behavior. And the other, is there a systematic way to find the Karl critical variable? So if you have a differential equation, then yes, it's a matter of scaling in the differential equation. If you don't have a differential equation, if you have just a series that you want to Borel sum, then the answer is also yes, in the sense that you can study the growth of the coefficients in some variable. And so this is related to one of the exercises. And you will see that if the growth is, say, 2n factorial instead of n factorial, that automatically tells you that you should have taken the square root of whatever variable you were using. And so you can actually discover these things fairly systematically, I would say, by studying the asymptotics of your original expansion, even if you don't know that this came from a particular integral or a particular differential equation. Oh, I lost you, David. I don't hear.
I beg your pardon. Thank you very much. I'm going to declare another break for 3 minutes to let the speaker rest.
Okay.
And those of us who are above the age of 70 also have to take bathroom trips, so we can't. We have to have
so at 5 past maybe, or something like that. Or?
Can I? Oh, there was.
Yeah. So I can't see, unfortunately.
Daniel Thompson.
Oh,
it was an accidental raised hand, but I had a question anyway, so
okay.
maybe I'll
Sure.
You mentioned that there was this phase transition at t=1 and that there was a strong coupling instanton and a weak coupling.
Yeah, so that's jargon. Are you asking about the jargon?
So I'm asking, is there some notion that one of these two instantons is becoming closer to the origin in the Borel plane or something like that?
Yeah, so it really is it's a Stokes transition in the sense that, first of all, these two functions are equal at t=1.
Right.
So there's a mention that the asymptotics is governed, if t is bigger than 1, the asymptotics is governed by an exponential involving this particular function of t. And so this, the value of this thing in the exponent is a function, it changes with t. But it's this particular dependence on t when t is bigger than 1, whereas the asymptotics is governed, on the other side by an exponential that looks like this, where this is now this function of t. So that's what I mean in the sense. Does that answer your question?
Yeah, no, it just resonated with something we'd seen with some like complex field configurations giving, competing instanton.
Yes, so it's exactly that. And so if you, in fact, if you go back to the original definition, you can rewrite this as an integral over eigenvalues, right? Eigenvalues of the unitary matrix or the corresponding Hermitian matrix. And so those eigenvalues, say, of the Hermitian matrix are real integrals to start with, right? And what you discover is that when n becomes large, as you vary t, which has nothing to do with those eigenvalue integrals originally, the saddles of those integrals, so this would be more in the language of what Chris was talking about, there is a genuine Stokes jump at large n, which goes through the point where t=1. And you change from the eigenvalue integrals being dominated by real saddle points to being dominated by complex saddle points. So I think that's very close to what you were suggesting.
Thank you for that answer. I'm concerned that we don't eat into the tutorial time. Remember that
Yes,
after
yes.
3 hours
yes.
of lectures, there are 2 hours of
Yeah.
tutorials to do.
Yeah.
So would you like to put up the slide for the next
Okay.
lecture and then proceed in your own time, Gerald?
Okay, so if I have permission to start, I have to, wait, am I sharing screen still?
I can see, yeah, how do I tell whether it's your third lecture?
Lecture 3.
Good. Yes, you're in business.
Okay, thanks.
You're
So
ready.
if I lose my voice, then okay.
Mm-hmm.
So this will be slightly more experimental, this talk. The motivation is that I want to discuss how these sorts of methods can be used in places where we don't necessarily have a starting point that is an explicit integral representation or an explicit differential equation. So that's a slightly different but obviously related question. So first of all, some obvious comments. Computing perturbative coefficients is difficult. You know, take a complicated problem, it's really hard to compute, say, in quantum field theory and some complicated nonlinear fluids problem. It's not easy to generate these expansions. And yet we've learned that there's this generic factorial and power type behavior underlying all this wide variety of problems. And we've learned that the power here is related to the location of the leading Borel singularity. And so that tends to dominate the asymptotics. The parameter here, B, tells you something about the nature of that leading singularity, whether it's a log or a algebraic power, or maybe it's just a pole. The parameter little a here relates, there's that recent question that relates to whether you have the appropriate expansion variable to be x or root x or whatever. And there's some overall constant, which is related to the Stokes constants and the overall normalization. So these are the interesting pieces of data from the coefficients that we'd like to extract because they have physical meaning in terms of the location of the singularity and the nature of the singularity, etc. So here's a slightly modified question. Suppose you have such a sum with some coefficients and in some variable, and these coefficients could be functions of some other variable, remember. How can we actually sum this accurately using Borel summation? I'm going to be talking about the Borel approach, but it's clearly complementary to the other approaches. And once we've summed it, how can we now take this expansion that was generated at x equals, say, plus infinity? How can we take it down to x equals 0? Say a high temperature expansion, taking it to a low temperature expansion, or a strong coupling expansion to a weak coupling expansion. And how can we extrapolate into the complex X-plane? Remember, in physics, using these Li-Yang arguments, we might want to do that. And how can we control some of these non-perturbative connection formulas that we've seen are so important? So these sound like very hard problems, but Resurgence is telling us that there's actually some global information buried in these local expansions. And the question is, you know, is that actually really, is that observation really useful in a particular case where we have very little chance of actually proving rigorously because we don't have an explicit differential equation? And the motivation will be to try and develop techniques that take advantage of the fact that the Borel plane structure don't tend to be particularly random. They tend to have some structure that we can maybe take advantage of. So the bottom line, if you remember nothing else from this lecture, the bottom line is that it can make a really big difference how we sum. And there are relatively simple procedures you can follow to squeeze more and more information out of this input formal series. And the basic toolkit is fairly simple. It's simple things like ratio tests and series acceleration methods. These are textbook material. Pade approximants, which is partly textbook material, but is also a very active field with a lot of interesting puzzles remaining. things like orthogonal polynomials in the large order asymptotics, and then classical things, continued fractions, conformal maps, and uniformization maps. These basic mathematical tools can be used in fairly simple ways to make a big difference to the precision we gain in summing this series and doing extrapolations thereof. So if we're going to do it in the Borel language, and the Borel language, of course, is, as I said, complementary to these other ways of doing it, but, and in the end, it's of course all the same thing, using different words and different formulas. The quality of the extrapolation of an asymptotic series is clearly governed by how well we can analytically continue the Borel transform function. So, we're making a transform from this function to this function. I think it's just essentially an inverse Laplace transform. And the reason you make a transform is to take a complicated problem, turn it into something easier, and then take it back again. So the step where we want to understand is how well can we analytically continue this guy? Because if we can do that well, then we can get a much higher precision extrapolation of this function. And lesson number one is it's much better to work in the Borel plane than in the original physical variable. So for example, you could apply Pade to this function here. It gains you something quite impressive, but you could also apply Pade in the Borel plane. Now, Pade is a nonlinear operation, and so they're not necessarily the same thing. And you can show that it's much better, and I can quantify that later, to do it in the Borel plane rather than the original variable. So the Borel plane structure in so-called natural problems tends to be fairly simple. We often confront situations where we have these integer repeated singularities, or sometimes only the n squared ones show up. In general, we might have different lines of singularities, but it doesn't typically occur to have some totally random distribution of Borel singularities. Now, obviously, that's not a very rigorous mathematical statement, but let's take it and run with it because it covers a lot of problems. So there's a beautiful technique that goes by the name of Pade Borel, so this is particularly aimed at the students who are new to this field. This is a really amazing approach to summation in a case where you don't really know much explicitly about the problem. So remember what Borel was. We have some series, we turn it into an integral representation. And so the problem now becomes to analytically continue this function from the limited amount of information we have about the original series. So the singularities of this function determine for us these non-perturbative corrections and the precision we can gain ultimately in the interesting regions which are really near these singularities. Those are the regions that we're most interested in probing. But of course, if you only have a finite number of terms here, this is a polynomial. So if it's a polynomial, it has no singularities. However, it develops singularities as n goes to infinity. Now, Pade Borel is a combination of the Pade approximation in the Borel plane. So you take this polynomial in T and you apply the Pade approximant to it, write it as a ratio of polynomials. I'll describe it in the next upcoming slides. And now you have some singularities. And this is incredibly easy to implement. And it gives you an excellent low resolution detector of the singularity structures in your problem. So let's review some of the features of Pade. So it's, first of all, very simple, it's very efficient, and it's a way to analytically continue this, for example, this function beyond its radius of convergence. It's a rational approximation. You take some polynomial and you write it as a ratio of polynomials where the orders of these polynomials add up to 2n, such that when you expand this around t equals 0, you have the same first 2n coefficients, but they can differ beyond that. So it's completely algorithmic and algebraic. The coefficients in these polynomials are expressed as some sort of determinants of the original coefficients. And there are clever algorithms to speed this up. And they're just built-in functions in things like Maple and Mathematica. So it's an absolute triviality to take a polynomial and turn it into whatever Pade approximation you want these days. The near diagonal Padets are often in applications the most interesting in terms of the recursion. And an interesting feature here is that the polynomials, the numerator and denominator polynomials, actually satisfy a three-term recursion relation. And interestingly, it's the same three-term recursion relation, but with different starting points. And that's a hint that there's a very deep connection here between Padet and orthogonal polynomials, which are built on three-term recursion relations. And that gives you a route into studying how these things behave as n goes to infinity, which is what you would actually be interested in studying the asymptotics. Because a lot is known about the asymptotics of orthogonal polynomials, dating back to the work of Szego and company. So for example, these are some comments of how to actually implement things. There's a problem with Padet that's easy to resolve, which is that if you go to very high orders in n and convert it to a ratio of polynomials, and if these, what very often happens is that these coefficients here in the ratio of polynomials, these coefficients can become very, very large. And that leads to a numerical problem. It's purely just a dumb numerical problem. It's not an interesting numerical problem. It's just a dumb problem that you're canceling very large numbers in evaluating this. And there's a simple resolution to this, which is just to convert to a partial fraction expansion, just by finding the zeros of this guy and then evaluating some residues. And so you see, you started off with 2n coefficients here. Here's the diagonal Padet, so you have n, capital N here and capital N here, or the same data is encoded in these n residues and the n singularities, zeros of this polynomial here. Of course, in principle, these are all equivalent, but this step from here to here involves a numerical step. Padet, when capital N is large, has this inconvenient numerical instability, but when you convert it to something like this, these residues don't tend to grow very rapidly, and the poles tend to be much simpler. So this is a more useful numerical application. There's also useful relation and interesting relation to continued fractions, which I can take this truncated series and convert it to a continued fraction representation. This is also a simple and algorithmic thing to do. This turns out to be very useful. This is somehow more stable in the large n limit, because if you do a Padet and you give me one more coefficient, I have to go back and start again and work out all these coefficients. Whereas in this continued fraction, I just work at the other end and do work out the extra one that I need. And so there's a deep relation between these diagonal and near diagonal Padet and the theory of continued fractions, about which a lot is known, which can be we can take advantage of. Perhaps the biggest problem that we confront is the fact that Padet by construction is a ratio of polynomials, so the only possible singularities it can have are poles, just by definition. So it's a rational approximation to the function, but the function you're looking for is probably not a rational function. So it may be, but in general, it will not be. We're very often interested in applications where it would have singularities that are not just poles, but branch points. For example, if we're working in the Borel plane, but even if we forget about Borel, forget about asymptotic series, just think about even studying things like phase transition points and critical exponents. Here, what you're interested in is finding the location of the radius of convergence, the nearest singularity, and finding what is its nature, the critical exponents. That's explicitly looking for branch points. Now, what does Padet do if you give it a function that has a branch point? Well, the first view of this is that it tries, here are some examples of 1 over 1 minus t to the 1/5. This is these blue dots. Padet tries to represent this branch point and branch cut as an accumulation of poles. So here, look at this one here. These are these blue dots. There's a whole set of poles here accumulating to the branch point at t equals 1. This one here, there's a line of poles accumulating to the branch point at e to the 2 pi over 5. Here, if I make the variable t squared, I see I have these oppositely aligned lines of accumulating poles. That's the way that Pade tries to represent a branch point and a branch cut. So that's both good and bad. It's good when there's some nice symmetry in the problem like this. You can, in fact, from the density of this accumulation, you can gain some information about the nature of the singularity. But we also confront problems like this, where there's two branch points that are complex conjugates of one another. I hope you can see this well enough. This is at e to the I pi over 3 and e to the minus I pi over 3. Okay, I'll deal with questions at the end if you don't mind. There are simple algorithmic ways to do these conversions. What Pade does, if you give it this function and you expand it, I think this was to say maybe 50 orders in T, it converts it to a set of poles that look like this. So you identify the branch points accurately or correctly, but it creates these interesting structures here. But the function itself that you started with has no singularities along the real axis. This structure is something that Pade just essentially made up because of this lack of symmetry. So that's interesting. We need to understand that. And that's actually turns out to be a very, very deep problem that, in my opinion, is not completely understood, even in the serious mathematics literature. There's a very beautiful formalism due to Stahl and results, not just formalism, theorems, that in the large n limit, as n goes to infinity, what Pade is doing here, it's trying to construct a so-called minimal capacitor. So here I have to appeal to some physics interpretation. It's constructing a domain of single valuedness in the complex plane with a boundary. So here what I've done is I've inverted T to 1 over T. It just makes this electrostatics analogy a little bit simpler. So this points out at infinity have gone to 0. These points have stayed the same. This arc has become this arc. Okay, so it's just the inversion of this expression here into the unit disk. So what Pade is doing is it's constructing a capacitor with these endpoints at the locations of the singularities and the one that was at infinity but is now at 0. And this is a capacitor here, which is the boundary of this domain of singularity. And the theorem is that what Pade does in the infinite limit, it arranges these poles in such a way that this capacitor has the minimal capacity with respect to infinity. So you can use all sorts of beautiful, simple electrostatics intuition to see what Pade does when it confronts a function like this. So here's an interesting application of this. Is imagine you're doing a problem where you want to identify a critical exponent and you think it might be a half. So you've got some function with some singularities and you think that the exponent is a half for some reason. But maybe you're not sure. Maybe you shift it by 10 to the minus 6. Well, Pade can tell the difference between this and this easily. If it's exactly a half, the line of poles will be like this. If you shift it by any small amount, it will break from this and form this minimal capacitor towards 0. There's something extremely special about the index a half, and I'll have more to say about that later, hopefully, if I don't run out of time. So there's this exquisite sensitivity that we can actually take advantage of using Pade. So the first exercise is, if you're not familiar with this Pade stuff, just play with it for a while. You'll learn all sorts of interesting things just by exploring what Pade does with certain types of singularity structures. The other problem, another problem with Pade, despite its incredibly useful and its high degree of simplicity, is that because it struggles to represent these branch cuts accurately and puts poles along the branch cut, it's not very accurate near the branch cut. It's very accurate elsewhere, but near the branch cut, it's not. And so if you're interested in probing that region, which is what we are interested in, if we're interested in looking at Stokes jumps and going from one Riemann sheet to another, etc., Pade is good, but it's not the end of the story. There are things that we can do are much better. And the other problem it has is that in a nonlinear problem, we've already seen that a Borel singularity would likely be repeated at twice the distance from the origin, and 3 times and 4 times. But if that's a cut, then what that means is that these genuine repeated singularities that are sitting on the cut, but Pade gives you a whole line of poles. So how do you tell whether that singularity is a pole or just part of the cut? Well, it turns out there's a very simple way to resolve these problems. And one possible approach that's also easy to implement and gives you a lot of information, and it's very, very simple, is to use a bit of conformal mapping. So this is also something that's classical mathematics that we know a lot about. So here are some possible configurations. For simple configurations of singularities and cuts, these explicit conformal maps are known. So you can take, say, the cut plane. There's a branch point here with a cut here, or if there's 2 cuts, or they could be the symmetric cuts, or I could have drawn one asymmetric cuts. We can map from this complex T-plane inside the unit disk in the Z-plane. So I didn't write the explicit maps. You can look these up in books. If it's a simple construction, these are all known. And this results in some amazing progress in the precision. So the idea, I'll call this a Pade conformal Borel method, is that you first make one of these conformal maps. So you do Pade first and you get some idea of what you think is the singularity structure in the Borel plane. And then you go back and you take your original problem and you make a conformal map into the unit disk, re-expand inside the unit disk, because now if you made your conformal map based on the radius of convergence corresponding to the leading singularity, then it will be convergent inside the disk, re-expand, and now do Pade inside the unit disk. So it's very simple, but it leads to an amazing improvement in the precision, which I will now quantify and show you some examples. And it's much, much better near the singularities, and that's why you get higher precision. So here's the Borel transform function of the Airy function that we talked about yesterday. Remember, we could write the Airy function as a Borel integral, where this was the Borel transform function. It has a branch cut from -infinity to up to -1. And so here I've rotated this so that we can actually see it. Here's the plot of the, I guess it's probably the imaginary part of this function, and we've got a cut from -1 to -infinity. So this is what Pade gives you. It gives you a bunch of poles along, accumulating at -1 along the negative axis. And these are trying to be this cut. And so you see that elsewhere away from the cut, it looks pretty accurate. You can check, it is very accurate. But in the immediate vicinity of this, it's not very accurate. So if you wanted to skim along the side of the cut using this, you're going to have all these fake oscillations, large oscillations, due to these poles that are just trying to be a cut. Now, suppose we do this conformal map first. So we take this thing, we do a low resolution Pade, and we think that there's a cut from -1 to -infinity. So we make the appropriate conformal map, something like this, flipped over, and then we do Pade. This is what we get. And it's completely smoothed out. You can hardly tell the difference. There is a small difference, but it's very, very small. And there's no pollution by these poles. And I stress that this is, it's almost a triviality to use this conformal map step before doing the Pade. And the improvement is dramatic. So here's another example of a simple branch cut function where Pade gives you this line of poles. This is if you do the conformal map, but don't do Pade. So the conformal map already gains you something, some higher precision, but doing Pade after the conformal map really gives you dramatically improved precision. We can plot this function along the cut. So just go shift by I epsilon above the cut. And so the blue line is the exact answer, and it's also the conformally mapped guy. The red line is what Pade would give you. So these are poles, but if you put your I epsilon, they get smoothed out, but they still big oscillations. And you just see that these are the approximations just with 10 terms of the expansion. You see that Pade gives you all this fake oscillatory behavior, whereas doing the conformal map, it's bang on the exact function. If we then now use this and do the Laplace integral to go back to the original x variable, then this is the sort of improvement that you can expect. So this is this one of these incomplete gamma function examples. The expansion generated at x equals infinity, just using 10 terms in the asymptotic expansion. So here I'm thinking of the physics application where, you know, the number of terms is fixed. It's not like in the mathematics world where you just say, oh, well, I changed the number of terms. Well, that's not possible in a lot of problems. This is the problem where the number of terms is fixed, but you want to still squeeze as much information out of it as possible. And the point is you can do much, much better than just the standard least term truncation type stuff. So the purple line is if you did Pade on the original 10-term polynomial. So that's a reasonable thing to do. And the dashed black line is with 1% precision to the exact answer, just to guide the eye. And you see that, you know, even this x Pade is pretty good. We get from infinity all the way down to x less than 1 with 1% precision. And given that it's a matter of just pressing the button and waiting for a nanosecond, that's pretty good. If we then do Pade on top, we go to the Borel plane and then do Pade, that's the red line. And we gain about a factor of 10 here in the precision. However, if we do also the conformal map and then do Pade, we gain actually an extra factor of about 100 here. And so that's the type of precision. And I stress that it's exactly the same input information. All you did was treat it in a different way. And the different ways of analyzing or summing are, you know, not that more difficult than one another, and yet the outcome is dramatically different. So we can actually quantify this using this Szego asymptotics techniques. So let's look at this generic factorial growth of the coefficients. I've normalized things so that the leading singularity is at 1. We can do that. We can, if we don't know the exact location of the singularity, we can actually use this as an iterative tool to refine our estimate of where that singularity is. But let's, for sake of simplicity, assume that we have normalized it in that way. So we still have this factorial growth that we're trying to control. And I'm thinking of taking n terms of this expansion, this factorial. So again, if you do x Pade, you can use these orthogonal polynomial results to show that the fractional error as a function of x and as a function of the number of terms you give me, capital N, scales in this exponential way. Whereas if you do Pade, you gain an extra factor of n up here. And so the way to read this is, this means that we're starting at x equals infinity. We would like to go down to x closer to 0. This tells me that as a function of n, the sort of minimal value of x where I can reliably extrapolate is scaling like 1 over n in this case, but like 1 over n squared in this case or this case. But if we do this conformal map and then do Pade, it's now scaling like 1 over n to the 4th. And you know, if n is 10, this is a big difference between where we can extrapolate to or not, as is shown in this particular example. There are subleading corrections there that can also be calculated. I've just put the leading behavior. And interestingly, the leading behavior doesn't depend on alpha. So that's a worthwhile lesson that we should take to heart. There's another advantage of this conformal mapping, is that if we look at one of these nonlinear problems, not these cases where it's just a single exponential integral or a single area function, but these nonlinear problems, say from nonlinear differential equations, or interesting exponential integrals, we have this problem that typically the Borel singularities will be repeated, but Padé has a problem seeing that. But the conformal map actually solves this problem as well. And the way it works, let me show you an example. Imagine you have this type of Borel plane structure. There's a singularity at, say, plus I and minus I. But we expect, because it's a nonlinear problem, that there will also be a singularity at 2i, 3i, maybe at minus 2i, minus 3i. But if we ask Padé about this problem, it'll just give me a line of poles here and a line of poles here accumulating to the leading singularity. And so how do I know that this one's a genuine pole and not just one of the ones that's trying to make a cut? So let's make the appropriate conformal map. Let's bring this two-cut domain here inside the unit disk. Here's the explicit expression for the conformal map. So Z is the variable in the conformal plane. So we'll work inside the disk. So you just take your original function, you re-expand it in terms of Z to the same order, and then do Padé. So this is what you would get if you just did the original Padé and the original variable P. You'll notice that before I was using T for the Borel variable. Now I'm using P because I didn't want to change the notation on some of these figures here. So here we see indeed that in this problem, I haven't even told you what this problem, where this is coming from. This is coming from a nonlinear problem. This is what Padé tells you. And you look at that and you would say, okay, there's a singularity at plus I and there's a singularity at minus I. And because of this accumulating pole pattern, I would guess that there's a branch point here and there's a branch point here. But you don't see anything funny happening at 2i or 3i or whatever. So let's just make this conformal map, because looking at this Padé, we would guess that that's the appropriate conformal map to make. And now this is what happens. It's analytic inside the unit disk, of course, by definition. But there are singularities outside the unit disk accumulating to points on the unit disk. And here's the image under the conformal map of the leading one. That's this point and this point. And this point here is the image of 2i. And this is the image of minus 2i. And this is the image of 2i on the other side of the cut. And likewise, we can see the image of 3i. So we can see poles accumulating to 3i. And with a bit of imagination, you can identify something at 4i. But the point is, this incredibly simple step of conformal mapping has immediately resolved this resurgent Borel plane structure into different regions in the Z plane that we can now probe independently of one another. So that's an incredibly useful step. It turns out there's an even better procedure that I'm not going to talk about today, which is that instead of this conformal map using a uniformizing map, and Ovidiu Costin is going to give a seminar Thursday next week where he will discuss some of these questions and talk about this uniformizing map technique. These things give you a super precise exploratory tool. So the sort of modus operandi here is you have some result of some calculation which you suspect is an asymptotic series, and you want to learn how to sum it, and you also want to learn how to sum it in a way that, first of all, is easy, and that you can analytically continue maybe to other regions of the parameter plane. So you might start with strong coupling and you want to go to weak coupling, or vice versa. You might start with high temperature and you want to go to low temperature, vice versa, but you might be going through a phase transition. So you have to worry about maybe some Stokes transition somewhere in the complex plane that you want to identify. And the point is, these techniques are basically probing the singularity structure of the Borel transform function. But of course, it's not the full Borel transform function. It's only the piece of the Borel transform function that you have, because you only have some number of terms. the idea is to somehow try to optimize the way you probe as precisely as possible in the complicated regions near the singularity. And it turns out there are various relatively elementary steps you can use to make this a still experimental, but very precise, and even under some conditions optimally precise probe tool, which can extract a lot of information from the input. I'm going to show you an example here now, and in the spirit of what we've seen so far, I'm going to pick yet another Penlevet equation. So Adri already talked about the Penlevet-1 equation, and you can get, using the techniques he described, you can also get incredibly accurate, what are effectively summations, solutions of the differential equation. I'm going to show it from the point of view of summation, in the sense that I'm not trying to solve the differential equation. I'm starting with an asymptotic expansion to the formal solution and trying to rebuild the function from the series. So it's sort of solving the differential equation, but through the route of a series expansion. So here's the Penlevet-1 equation. It has a quadratic nonlinearity and just an x term. Looks fairly innocent, but it has an amazingly rich structure to it. The appropriate variable, somebody asked about the finding the appropriate scaling variable. There are a couple of tricks you can use. One is just scaling in x. You put in some ansatz for the power of x and just start matching terms. You very soon discover that x to the 5/4 and 5/2 are special. Or you can actually, what I'll show in a little bit is you can just put in an exponential ansatz and it'll tell you what the appropriate power is. In any case, from matching these two terms, there's a natural square root type behavior. There's a plus or minus because this was y squared. I'm going to choose the minus. That turns out to be important. And then you can now convert this differential equation into a recursion formula to generate these coefficients here. And here are the first few terms. And the various choices I've made here define this so-called Triton-K solution to Penlevet-1. So again, this is a very special, finely tuned solution to the Penlevet-1 equation, where this fine tuning achieves is the minimal domain of poles in the solution. So it's like, remember, this has some asymptotic Weierstrass P function behavior. So for the completely general solution, there are poles all over the place, and asymptotically they're on a lattice, but they're just everywhere. But if you fine tune your boundary conditions in a very delicate way, you can push some of those poles off to infinity. And this Triton-K solution has a very interesting pole structure that I'll show you in a little bit. Anyway, we can generate this input data very easily. Here I've shown you a few times. I'm going to be interested in the case where n is not something completely crazy, maybe 10, and see from those 10 input coefficients, what can I tell about this actual function in the complex plane, not just near x equals infinity. So here's an exercise. So first of all, here is show that the Écart critical variable is this by a scaling argument. Once you know that with an ansatz, you can convert the differential equation into this recursion formula and generate lots of these. And then you can numerically resolve the large order growth of the coefficients. And you can even resolve the Stokes constant, which is known in closed form, from this large order growth analysis. And that's the reason why yesterday in the ARAW example, I asked you to do this numerically, even though in that case it was unnecessary, because there was a simple closed formula for Cn, the coefficients, just as ratios of some gamma functions. So the large N expansion is a triviality. Here, there is no closed formula, but there is an explicit recursion formula. So you can solve the problem numerically, analytically, to a very high order, just by generating lots of these and doing some glorified ratio tests on these. Now, if you just do this asymptotic expansion in X and truncate it at, say, 10, 20, 30, 40, 50 terms, this is what you get. The blue line is the exact tree-truncated solution along the real x-axis. And we see the typical behavior of an asymptotic series, that it seems counterintuitive that the getting more terms in the series, the answer is sort of getting worse at small x. But that's just because truncating at some fixed order in n independent of x is just not the right thing to do with an asymptotic series. So the Penlevet-1 equation has a nice symmetry. Remember that the Penlevet-2 equation had this nice pi/3 symmetry that it inherited from the area equation. The Penlevet-1 equation has a 5-fold symmetry. And this so-called tree-truncated solution that I'm studying here has this property that in the complex x-plane, remember x is the variable in the differential equation, and we're developing an expansion around x equals plus infinity. It has this Stokes structure. There's an anti-Stokes line along here for the tree-truncated. This is a Stokes line at, what is it, pi/5, 2 pi/5 here, 4, what am I, 3 pi/5, 4 pi, right? No, sorry, 2 pi/4 pi, sorry, can't count. The shaded region in here between 4 pi/5 and 6 pi/5 is the region in which this particular tree-truncated solution has its poles. It's completely free of poles in these regions. It has interesting Stokes transitions as you cross this line, as this line, and this line, and this line, and come back. These are nonlinear Stokes transitions. And the question I'd like to ask is, forget about the differential equation now. If you just gave me the coefficients from this expansion, just gave me those numbers, and maybe you're testing me and only giving me 10 of those numbers, would the expansion actually know anything about this? Now, this sounds like a somewhat foolish question, but one of the sort of motivations for studying resurgence is that maybe something like this is actually possible, because the idea of resurgence is that these formal asymptotic expansions actually know something about the full transeries structure of the solution. So this is my goal now, to study what happens in these various interesting directions. So here's another, this is actually a very simple exercise, just show by a scaling argument why this fifth root of unity is so special, leading to this pi/5, 2 pi/5 type structure. So now let's just do the natural thing. Let's take this truncated series, let's convert it to a Borel transform by dividing by some appropriate factorial, and then just analyze this function. And what we're interested in is learning about its singularities. So we need to know some analytic continuation of it in the complex Borel plane. Remember, P here now is my Borel variable. And so the first thing to do is to do this Borel transform. This is extremely easy and gives you a lot of information very quickly. And so the poles of this thing, which come from the zeros of Q, obviously, are going to tell you something about them. And this is what you get. And I guess this is a plot for 50. I thought I had a plot for 10, but you just have fewer terms here. So this is what I showed you before. There's accumulating towards I and minus I. So just looking at this, you would immediately make a guess that there is a singularity, which is a branch cut from I to I infinity and from minus I to minus I infinity. You make that conjecture based on this numerical evidence and proceed. If that turned out to be a wrong conjecture, you should discover it very quickly in the subsequent analysis. So first of all, if I just have the truncated series, so the truncated series is this black curve here. Remember that was from this one here with 10 terms going up like this. But the blue dashed curve is after doing this pas de Borel in the Borel plane and then doing the Laplace integral to come back to the x variable. And the dotted line is the exact tree-truncated behavior near x equals 0. And so you see that even with 10 terms of this expansion about infinity, and with this incredibly simple pas de Borel transform step, you can get very, very close to extrapolating down to 0. from that input information without knowing what the differential equation is, just knowing the coefficients. If you now do this conformal mapping step before doing the pade, so you look at this and say, I should make a doubly cut conformal map maybe into the conformal disk and then expand and then pade, you now get what is the solid blue curve. The dashed here is if you just did the pade Borel, and the black dotted line is the exact answer. And so you see there's increased precision as x goes to 0 here from this conformal mapping step. We can look at the higher singularities in the Borel plane. Remember, this is a nonlinear differential equation, even though you might not have known that because all I did was give you the coefficients. I didn't give you the differential equation. Do those coefficients know that it's coming from a nonlinear problem rather than a linear problem? You wouldn't be sure looking at this sort of structure in the Borel plane. And in particular, if you try to plot along the edge of this would-be cut, you see this. This is the real and imaginary part here. I guess this is 50 orders in the Borel. So you see the leading singularity at 1 on the imaginary axis, so at I. But then this pade is trying to represent the cut by all these poles. And it's not clear that anything special is happening at 2 or 3 or whatever. So there's no sign yet that this came from a nonlinear problem. However, just make a conformal map before you do the pade. And this is now what you get. So the red and the blue are the real and imaginary parts. This red is the imaginary part, blue is the real part, skimming just next to the imaginary axis. And now the leading singularity 1 is resolved much more precisely. And you also see the next singularity at 2. And if I change the scale on this axis, you would also see a blip at 3. You can't see it at this scale, but you can zoom in to see it. And in fact, you can look in greater detail because if you assume that this is coming from a resurgent problem, and by studying the leading singularity, you evaluated the Stokes constant by looking at how the function behaves as you approach the singularity, how the Borel transform function behaves as you approach the singularity. Turns out you can identify that Stokes constant at extremely high orders from if you use this conformal mapping technique. And now if you just assume that this problem is not only nonlinear, but also resurgent, then there's a prediction of what this jump here should be. And it should be half that Stokes constant squared, which is this number, which is what this jump here is purely numerically. And this is just coming from a low order number of terms, here 50 for this plot in the asymptotic expansion. And the only information used at this point were the coefficients. Nothing was used about the differential equation or the analytic properties of this true truncate solution. Now we can push it all the way down to 0. There's a way to do that. I'm not going to go into all the details, but we can get a ridiculous degree of precision at 0. So integrate from, well, not integrate, extrapolate from x equals plus infinity all the way down to 0 using, I think here, 50 terms, and there's 65 digits of precision, which is much better than standard numerical techniques going along the real axis. Now we can, so we've gone from infinity down to 0, but maybe a more interesting thing to do is to zip around like this and probe this so-called Dubrovin conjecture that the poles only lie in this 2 pi over 5 wedge, which incidentally was proven in 2012 by Vidyu, Kostin, and Huang and Salo-Tanvir. And we can just probe this question numerically, whether this expansion here knows about this fact. And indeed, here are the poles in red that you extract from this numerically extracted solution, which started off life as a polynomial out here. And somehow in this region, under this extrapolation, turned into a meromorphic function with a more or less regular lattice of poles, And the black dots are the predictions of transasymptotics, the leading transasymptotics prediction, which is supposed to be good way out here and are remarkably good even down here close to the origin. Incidentally, if you use that uniformizing map instead of the conformal map, you get much more information and much more accurate information about these, this pole region. And I stress again, it's exactly the same input information, just a bunch of coefficients. And it's just a question of how you choose to process those coefficients in your resummation. And none of the steps is difficult. One last test precision test before we finish. Remember that this is supposed to be, in general, a meromorphic function in the complex plane, and yet it started off life as a asymptotic expansion in a trans series along the x goes to plus infinity line, and yet somehow in this region it's supposed to turn into a meromorphic expansion like this. In these regions, those poles have all been pushed off to infinity, so you don't see them. But in this region, you should see them. And remember that the location of the pole and the next constant completely characterize the solution. Those are the two parameters that define the Tritonquet solution. And I can choose any one of these poles, and any one of those poles has a location and a second constant. And for any one of them, that fixes the solution. But we might as well choose the closest one to the origin. It's a natural one. So here's a very high digit precision determination of those locations using these techniques. And now we can test this precision. We can just take a solution and expand it near this pole. And so remember, we don't yet know the equation, but the equation tells you that this is what happens. That the first coefficient, first of all, there is no linear term. That coefficient must be 0. This thing has to have a coefficient which is this divided by 10. The next coefficient must be 1/6. The next coefficient is this extra constant. And the next coefficient is 0. And then the next one is this thing squared. So this is what happens with 50 input terms. It's precision beyond 30-digit precision. This coefficient is 1. The next coefficient is 0. The next coefficient is 0. The next coefficient is this location divided by 10. The next coefficient is 1/6. The next coefficient is this extra variable. The next coefficient is 0. The next coefficient is this pole location squared over 300. So this is what I mentioned about using Painlevé type equations to probe these extrapolation methods in order to be able to do extremely high precision extraction. So what this means in effect is, in this case, from the coefficients, I could have reconstructed this expansion in the pole region purely numerically. And from that, I can immediately write down the differential equation that the problem came from. Right? So this is a reconstruction problem that, to some degree of precision, is extremely accurate just from the input information. So I think I'll stop there. Thank you. So there's the overall conclusion. Okay.
So we have a question already, which I will paraphrase. I will paraphrase it as follows.
Oh, I can read it, I think.
Yeah, but how much of this could you do for people who don't want to think, but just pay money to Mathematica and Waterloo? Which of those steps in the final problem required brain power rather than just pressing a button in Mathematica?
Okay. So there are algorithms for computing both continued fraction representations and Padé. They involve determinants. So, to a certain degree, some of this you could do by hand, so to speak. You can easily, if you have access, you can write your own C program to do these to whatever level of precision you want. The algorithms are out there. It's not, this is very, very well studied. They're a very efficient algorithm. So if you want to do it symbolically, using Mathematica or Maple, that's the optimal way. If you want to write your own symbolic program, I guess that's possible. I wouldn't know how to do that, but I think people do. And you can do it in C with some chosen level of precision. The algorithms are not difficult.
Thank you.
Okay,
There's another question. Another question.
Yes, so the answer is yes. There is a link between the residue. So this is referring to, say, this Pade conversion into a partial fraction expansion. I mean, yes, there's a very precise relation between the behavior of the residues and the sort of density of accumulating Pade poles, and to the nature of the branch cut.
Okay, well, I don't see any more questions, and we're past the hour of
Yes.
5. So I want us to thank Gerald again. Thank you. Well done for keeping your voice as well as our attention. And now the important thing is that in chat, I'm going to check. Will you all go to chat? And there you should see the Zoom link for the tutorial session. Okay.
Okay.
I think that concludes the business.